lecture 27 of our series on numerical methods in civil engineering, we will continue with our discussion on differential operators. Recall we considered operators operating on a sequence y is equal to y0, y1 through yn, and we defined two operators. We defined the shifting operator which we denoted as E, and which operates on each term of the sequence and shifts it to the right, shifts each term to the right. And we also define the difference operator delta, which creates a new sequence by taking the difference between each term in the sequence and its next term, right. So, for in the 0th position we had y0 in my original sequence. In the new sequence it will be y1 minus y0. So, the term on the right minus the original term. Similarly, for other terms in the sequence. It can be shown that k operations of the differential operator delta lead to a new sequence, the n plus 1th term of which is represented by the action of delta k times on the n plus 1th term in the original sequence yn. So, the n plus 1th term in the original sequence is yn, right, because it starts from y0, and what I am just saying is that if you operate k times on that operator, right, that is the resultant sequence is the action of delta k times on the n plus 1th term in my original sequence, which was yn, right. So, the result is as you can understand, if you operate k times on the yn, right, you are going to get more and more terms, because first time when you operate delta on yn, you are going to get yn plus 1 minus yn. If you operate again on that, so you operate on yn plus 1 as well as yn, right. Similarly, the terms become larger and larger, and eventually the result of operating k times on yn with the delta operator can be represented by something like this, right. We saw this expression last time, and we also tried to give a proof for that using induction, right. So, here I am just mentioning the final result, right. Okay, so that was where we stopped last time. Now, let us take a step back and recall that delta y is equal to yn plus 1 minus yn, and since Ey is equal to yn plus 1, we can write symbolically delta y is equal to E minus 1y, because E operating on y is going to give yn plus 1 minus yn. So, that is the equivalent to the operating on yn with delta, right. So, we can write this delta is equal to E minus 1, right. We can write delta is equal to E minus 1, and using this symbolic notation, the above theorem meaning this result, right, this result can be written as delta k is equal to E minus 1k, because they are equivalent, right. So, we can write this as well as E minus 1k operating on yn, right. Okay. So, sometimes it makes it yields a lot of insight if we look at a sequence y0, y1, y2, y3, y4, and then see the results of operating on this sequence repeatedly with the delta operator and arrange the terms in this fashion, right. So, here what I have done, I had originally y0, y1 through y4. First I operate on this, right. So, delta y0, right, that is equal to y1 minus y0, delta y1 which is equal to y2 minus y1, delta y2 y3 minus y2, and delta y3 y4 minus y3. So, that is after I operate first on with ones, right, with the delta operator with the difference operator once, right. Then if I operate again, right. So, let us see what del 2 y0 would be. That would be del y1 minus del y0, del 2 y1 would be del 2 y2 minus del y1, del 2 y2 would be del y3 minus del y2. Similarly, if we operate 3 times, so del 3 y0 is going to be del 2 y1 minus del 2 y0, del 3 y1 del 2 y2 minus del 2 y1, and del 4 y0 is del 3 y1 minus del 3 y0. So, if we arrange these sequence, this difference, the action of the difference operator on the sequence, the repeated action of the difference operator on the sequence in this fashion. sometimes it yields a lot, it gives a lot of insight. For instance, in the next problem, right, suppose my original sequence was 0 0 0 1 0, right, and I operated on that repeatedly with my difference operator, and you can see that after I operate first time I get 0 0 1 minus 1, second time I get 0 1 minus 2, third time I get 1 minus 3, fourth time I get 9 minus 4. So what does this tell me? This tells me that if my original sequence was actually 0 0 0 0 0, right, and then I introduced a minor perturbation to that sequence in the fourth term in the sequence, right, I made it 1, right. So if my original sequence was 0 0 0 0, all the terms were 0 in my sequence, if I operated on that sequence with the difference operator 4 times, what would I get? I would still get 0, right, del 4 by 0 would still be 0, right. But then if I introduce a minor perturbation, one term in the sequence undergoes a slight change, it changes from 0 to 1. In this case the fourth term in the sequence changes from 0 to 1. Then if I look at the difference way down the road after I have taken repeated differences, you can see that the difference is much larger, right, it has become amplified. That minor change, that change in the fourth member of the sequence, that change in 1 has now become minus 4, right. So this shows the effect of perturbation in one element on the sequence, which changed by just one element, then after a difference operator it has grown 4 times, right. So this tells us why, in any numerical method you will see that if you look at the derivative, the error in the derivative is always higher than the error in my original variable, right. For instance, if I know many of you are familiar with the finite element method, where suppose we have the primary variable as the displacement, right. So and then we are interested, we look at the results of the solution, we look at the displacements, we look at the strains, we look at the stresses, right. So suppose there is an error in the displacement and then we look at the error in the stresses, the error in the stress will always be higher than the error in the displacement, right. Whether the error in the displacement is due to discretization error or it is just a truncation error, right, the error in the derivative will always be higher, right. This exactly shows why, right, because repeated operations of the difference operator, right, it always multiplies, it always scales, magnifies the error, right. So this sort of approach allows us to study the effect of errors in initial data on derivatives if, there is a big if here, if we can relate the derivatives to the difference operators. I have shown this for the difference operators, but then if we have to claim, if I claim this for the derivatives, I have to relate the derivatives to the difference operator, and it turns out that we can do that, right. So the same thing carries over for derivatives, right. An error in the initial data, it gets multiplied, it gets scaled several times. The more times you take the derivatives, the more is the error scaled by, right. It also leads to the conclusion that the error in the derivative is always higher than the error in the initial data. Now, up till now we have looked at difference operators on a sequence, right. We can as well apply these difference operators on a function, right. So in case of a known function, evaluation of successive higher order differences leads to the following conclusion. We can show that also. It is seen that differences decrease rapidly as the order of the differences increase, until the differences become small enough that round off error dominates, right. So it's found that if instead of a sequence I look at a function, right, if I take repeated differences, right, if I take repeated differences on a function, it is found that the differences decrease rapidly, right, the differences decrease rapidly, and then until finally the differences are only different by the round off error, right. So if in my original function values I had certain round off error, then after repeated differences what is going to show up is just the round off error, right. Such behavior is typical of different schemes of well behaved functions, right. In the following table, which shows the evaluation of successive difference operators of the function sin x. So, we are looking at the function sin x over the range x belongs to 1.30 and 1.36, and we are evaluating it at step sizes of 0.01. We can see that after we take the fourth difference, it is totally dominated by the round off error in the values of y. Let us look at this little table, right. So, here now we are looking at difference operators on a sequence, on a function rather than a sequence, and the function that we are considering is sin x, and I am evaluating that sin x over an interval from 1.30 to 1.35, and I am evaluating it at steps of 0.01. So, 1.30, 1.311, these are my values at which I am evaluating the function sin x, and these are the values, the results of sin x, right. These are the results of sin x, and here I have taken the difference, right, the difference between this and this and this and this and so on and so forth, right. And then I have taken the difference again, right. So, in this case this minus this becomes that, this minus this becomes this minus this becomes that, right, and then I have taken the difference a third time, right. You can see that these are becoming smaller and smaller, right. These magnitudes are becoming smaller and smaller, right. The magnitudes of these differences are becoming smaller and smaller until they are so small that this may be as small as the round off error involved in the calculation of this, right. If we have calculated this with a round off error up to the fourth decimal place, right, then this difference is the same as the round off error which I used in my calculation of this sin x, right. So, this may become as small as the round off error, right. Is that clear? So, I hope it is clear, right. The first thing that I talked about was the fact that when you have a perturbation in the initial data, right, when you take repeated difference, that perturbation gets amplified. So, that means that when you have an error in the initial data, that error becomes amplified. But here I am saying that when you have a certain function that you are evaluating at certain intervals, at a certain fixed interval, if I take repeated differences, those things become smaller, those differences become smaller. It does not say anything about the error, right. The error might, if there was an error here, if there was an error in the calculation here, right, when I take repeated differences, that is also going to get amplified, right. That is for sure, that holds every time, right. All I am saying here is that these differences, these magnitude of these differences are becoming smaller, right, but the error can become larger, right. If there were an error there, that is going to get magnified. This is the actual difference, right. The actual difference is becoming smaller, but the error, if there was an error in my calculation of sin x somewhere, then when I do this repeatedly, that error is going to become larger and larger, right. That is why when I say that this is equivalent to the round off, that means that is actually reflected by that, right. So, if there was a round off error in the calculation of sin y, if I take repeated differences, that round off error is going to get multiplied, it is going to become larger, it is going to get magnified, right. But now when I take the repeated differences, the function value, the difference value is also becoming smaller, right. The difference value is also becoming smaller. The actual, so that round off error, if it is increasing, it may become actually larger than the true difference, right. It can become larger than the true difference. Is that clear? I hope I did not confuse you. So, as the above example shows, difference operations can be applied fruitfully to functions as well as sequence. So, E and delta relate a function f evaluated at a certain, so it is very similar, so I do not want to belabor this, but this is very similar to how we operate on sequence. So, E f of x is nothing but f of x plus h, right, x evaluated at the after I move one step forward, right. So, if I have uniform grid, if I have a uniform grid, if E f of x is f evaluated at x plus next point at the next point on the grid. So, f evaluated at the next point on the grid, which is x plus h, right. Similarly, delta f(x) is equal to f evaluated at the next point on the grid minus f evaluated at x, right. Similarly, we can evaluate higher order differences, right. So, del 2 f(x) is equal to del f(x). I operate on del f(x), I operate on f(x) with the difference operator, and then I operate again, right. So, operating on f(x) with the difference operator, I get f(x) plus h minus f(x), right, and then I operate again with the difference operator. So, I operate first on f(x) plus h. So, then I am going to get f(x) plus 2h minus f(x) plus h minus del operating on f(x) will give me f(x) plus h minus f(x), right. So, that is what I am going to get. If I pull the terms together, I get f(x) plus 2h minus 2 f(x) plus h minus f(x), right. Similarly, del square f(x) minus h is given by this. Same logic, right, x minus h, del f(x) minus h is equal to f(x) minus f(x) minus h, then operate on that with del again, I get that value. So, it is important to note that for functions unlike sequences, the values of the difference operator depends on the step size, right, it depends on h, right. Remember, for sequences it only depended on the function value, on the various terms in the sequence, right, on the depended on yn plus 1, y0, y1, right. Now, it depends not only, it depends on the step size, right, it depends on the step size. Next, we look at the following results, which states that if f is a polynomial of degree m, then del kf for k lesser than or equal to m greater than or equal to 1 is a polynomial of degree m minus k, and delta m plus 1 f is equal to 0. If you think of derivative, this should be familiar to you, right. If I have a function which is a polynomial of degree f, right, and I take the derivative k times, then the order is reduced to m minus k, right. Think of a polynomial x to the power n, right. If I take the derivative k times, then I have the term will become x n minus k, right. So, the same thing holds for the difference operator, right. What it is saying that if f is a polynomial of degree m, then if I operate on that function k times with the difference operator, then I am going to get a polynomial of degree m minus k, similar to what I would get if I operated with f k times with the differential operator, right, instead of the difference operator, right. And then if I operate m plus 1 times on f, I am going to get 0. Think of a polynomial of degree x to the power m. If I take m plus 1 derivative of x to the power m, I am going to get 0, right. Similarly, exactly the same thing happens for the difference operator, right. To show that, well, we can show that for k equal to 1 by using Taylor's theorem, right. So, delta f(x) is equal to f(x) plus h minus f(x) by definition, right, and then I expand f(x) plus h about x in Taylor series, right. So, what do I get? I get f(x) plus h f prime of x, so f(x) cancels, and I have h f prime of x plus h square factorial 2f double prime of x through h m factorial m f m, the mth derivative of f evaluated at x, which it is clear is a polynomial of degree m minus 1, right. It is a polynomial of degree m minus 1, right, because the leading order term is given by this h f prime of x, and that is the first derivative of the polynomial of degree m. So, that is a polynomial of degree m minus 1, right. So, this term will be m minus 1, that term will be m minus 2, and so on and so forth, right. So, what does this tell me? That if I, and this is actually equal to that, right, this is exactly equal to my difference the result of my difference operation, right. So, this tells me that if I take the first difference of f x and if f is a polynomial of degree m, then delta f x is going to be a polynomial of degree m minus 1, right. And for higher orders of k, we can prove it similarly by induction. The main significance of difference operators is connected to the fact that differentiation is a limiting case of forming differences by applying difference operators, right. So, the difference operators, as I make this step size, as if I consider difference operators operating on a function and I reduce my step size, I reduce my h in the limit that h goes to 0, it can be shown that my difference and derivative operators become very similar, right. So, that is why they are useful, right. That is why these difference operators, when we solve a differential equation numerically, we can use these difference operators to approximate my differentiation operations, right. So, as the step size approaches 0, the results of difference operations approach the results of differentiation. The question is, how fast is the rate of approach? Number 1, how fast does the difference operator approach the derivative as h goes to 0, number 1, and number 2, how does the rate of approach change with the order of the difference, order of the derivative, right. Is the rate of approach the same for the first order difference operator and the first order derivative, and the second order difference operator and the second order derivative, the third order difference operator and the third order derivative. Before we look at this, we first consider the following analogous operations which are very similar to when you first look at derivatives, right, you look at things like derivative of a product, right, and things like that, right, derivative of an exponential or derivative of something raised to the power something, right. So, we looked at those derivatives first when we looked at derivatives like in high school or somewhere, right. So, now I want to look at very similar operations using the difference operator. So, I want to apply the difference operator on a product, right. I want to apply a difference operator in exponent and see the result and look at the result and compare to what I would get if I apply the derivative on those same things. So, if I apply the difference operator on a product, how does the result compare to the derivative of the same that same product, right. Let us look at that. So, if I look at the difference of a product, right. So, I have a product UNVN, right. I have a product UNVN and I am operating on that with the difference operator. So, by definition, this is going to be this thing evaluated at n plus 1 minus this thing evaluated at n. So, that is going to be UN plus 1 Vn plus 1 minus UN Vn, right. So, I can write this as UN Vn plus 1 minus Vn plus Un plus 1 minus Un Vn plus 1, right. You can see that the only terms that are going to be going to survive are going to be Un plus 1 Vn plus 1 and Un Vn. This term Un Vn plus 1 and Un Vn plus 1, they are going to cancel out because they are going to negate each other, right. So, I can write it like that, right. So, let us compare this result with the formula for the derivative of a product uv. Derivative of a product uv duv is equal to u dv plus v du. Now, look at this. If we think of this as del v, right, as del v, so I have u del v plus, if I think of this as del u, del operating on un, right, del un and this as del vn. So, I get del un Vn plus 1, which is very different, right. You have duv is equal to u dv. So, this term is similar, this term is similar. Then you have un plus 1 un, you can think of that as du, analogous to du, but then here it should have been Vn, right, but it is actually Vn plus 1, right. So, there is that's the difference, right. So, in the difference formula, the second term contains Vn plus 1 rather than Vn, which is different from the differential formula, right. This tells us that this operation is not exactly equal to the derivative, right. This difference operation is not exactly equal to the derivative, right. It will become close to the derivative when my n plus 1 is very close to n, right, when my Vn plus 1 is very close to Vm, right, when my step size is small, but it is not exactly equal to the derivative, right. So, that is the point I want to emphasize, right. Let's look at the difference of an exponent, right. So, del Ca to the power x, if I evaluate that, so by definition that is equal to the function evaluated at x plus h minus the function evaluated at x, right. So, that is equal to Ca x to the power x plus h minus Ca to the power x, right. So, I pull out Ca x, I get a to the power h minus 1. I can write this as CAH minus 1 into a to the power x. So, by induction, if I operate on this k times with the difference operator, I can show that this becomes CAH minus 1 to the power k times AX. Now, see what you would get if I used exact differentiation. D a to the power x would have given me AX ln A, right, which is very different from the difference formula which we calculated here, right, which is very different from. So, you can see that difference operators and differential operators are not really identical, right, even for very simple operations, right, most elementary derivatives, right. Here also the difference operator is giving something which is not really the same as the differential operator, right. Next, we consider the result obtained when a difference operator is applied to the members of a sequence W0, W1, W2 through Wm, and it means W3, W4, Wn. Sorry, I missed the ellipses, right, and the result is summed, right. So, if I operate with the difference operator on this sequence, if I operate on the first term, I am going to get delta W0, which is going to be W1 minus W0 plus, and then I am adding the result, right, and the result is summed, right. Then I operate with the difference operator on W1, so I get W2 minus W1, operate with the difference operator on W2, I get W3 minus W2, and so on and so forth, Wn minus Wn minus 1, right. I get this, right, and you can see that if I add them together, I am left with Wn minus W0, right. But the left hand side is nothing but sigma n is equal to 0 n minus 1 del Wn. Why? Because this is del W0, which is this term, plus del W1, which is that term, and then del Wn n minus 1, which is this term, right, which is this. This actually should be small n, right, this should be small n, which is that term, right. So, the left hand side is actually this, and the right hand side is Wn minus W0, right. Now, we assume that Wn is actually given by the product of two terms u and vn. So, each term in this sequence W0 is given by the product of u and v. So, W0 is equal to u0 v0, W1 equal to u1 v1, and so on and so forth, right. So, Wn, so let us assume that Wn is equal to un vm, then what do I get? The left hand side becomes sigma n equal to 0 to n minus 1 delta un vn, and that must be, that by definition, so that is equal to Wn is equal to un vn minus W0, that is equal to u0 v0. But by definition, delta un vn is equal to, not by definition, but just from our previous result, right, which used the definition, right. Let us look at that previous result, that is this, right, delta un vm is equal to un delta vn plus delta un vn plus 1, right. So, that is that, right, un delta vn plus delta un vn plus 1, right. So, we can write n equal to sum n equal to 0 to n minus 1 delta un vn is equal to sigma. So, I am just taking the summation and then I am replacing this by that, right. So, un delta Vn plus sigma n equal to 0 to n minus 1 delta un Vn plus 1, and I know that this must be equal to this un Vn minus u0 v0, right. Now, I am going to collect terms. So, from the above we get sigma un delta Vn, this term is equal to un Vn minus u0 v0, and then I bring this term to the right, minus sigma n equal to 0 to n minus 1 delta un Vn plus 1, right. So, I just brought one term to the right and I get this thing. So, sigma n equal to 0 un delta Vn is equal to un Vn minus u0 v0 minus sigma n equal to 0 to n minus 1 delta un Vn plus 1. Compare this with the integration by parts, right. So, if I integrate u dv within the limits a b, then the integration by parts rule tells me that this is uv evaluated at b and a, right, difference between b and a, minus integral a to b duv, right. Look at this, this is very similar. So, this is u dv, right, if you think of delta as d, right. So, un delta Vn u dv is equal to un Vn, so at the evaluated at the other end of the interval, minus u0 v0 evaluated at the first point in the interval, right, minus integral of a to b duv, right, del un Vn plus 1, right. Very similar except for that difference, right, that is Vn plus 1 and here I have V, right. So, if it had to be exactly analogous, this should have been Vn, right, this should have been Vn, but it is similar, right. So, next we introduce a result which formally establishes the relationship between the difference and the differential operator and the derivative operator. So, what is that result? That result tells me that if I operate on the function f of x k times with the difference operator, then I get h to the power k, h being the size of my step size, times the function f, the kth derivative of the function f, but that kth derivative is not evaluated at x, it is evaluated at xi, right, which is very, very important, right. It tells me that if I operate on the function f k times, right, I am going to get something very similar to the kth derivative of f, right. I am going to get something very similar to the kth derivative of f, but the kth derivative of f not evaluated at x, the point at which I am taking the difference, but at some other point xi, right. And what is the range of xi? What is xi? Well, xi can be any point which belongs to the interval x to x plus kh, right. Xi can be any point which belongs to the interval x plus kh, right. Of course, this assumes that the kth derivative exists, so that the function has k derivatives up to order, continuous derivatives up to order k, right. So, this is very, very important, right. It tells me that, well, if you take k differences, we are going to get something like the kth derivative, but not at the same point. It is evaluated at a point which is shifted, which may be shifted from the original point, right. And the extent of the shift is of course going to depend on your step size, right. It is going to depend first on the step size and also on the order of the derivative. The higher the order of so if I take the same step size and I look at higher and higher differences, so the shift, the range of the shift becomes larger because it is getting multiplied by k, right. So, for the first derivative, the point, the exact the derivative will be evaluated at will belong to any interval between x and x plus h. For the second derivative, it can belong to any interval between x and x plus 2h. So, as you take more and more derivatives, the range becomes larger, right, the range becomes larger. but if you reduce the step size, again the range becomes smaller, right. So, as you increase the derivative, the range becomes larger. As you reduce the step size, the range becomes smaller. So, for k equal to 1, this means that delta f x is equal to h of f prime of xi. Let us go back and take a look. So, delta f x is equal to h times f prime by the first derivative of f evaluated xi. So, it is not equal to h f x, right. That is very, very important, right. But recall that delta f x is equal to f of x plus h minus f of x. Therefore, we have f of x plus h minus f of x is equal to h times f prime of xi, and I know that xi must belong to the interval x to x plus h, which is nothing but my mean value theorem, right, which is nothing but my mean value theorem. So, to prove the result for k equal to 2, we use Taylor's formula to expand f of a plus h and f of a minus h, right, and we will define a in terms of x later on, but for the time being let us look at f of a plus h and f of a minus h. If I use Taylor's formula on f of a plus h, I get f evaluated at a plus h f prime a plus this term, this remainder term, where the xi 1 belongs to the interval a and a plus h, right, because I am evaluating it about a, right. So, xi 1 belongs to the interval a to a plus h. Now, let us look at f of a minus h, which is equal to this term plus this term, and xi 2 must belong to the interval a minus h to a, right, a minus h to a, right. So, we have xi 1 belonging to a and a plus h, and xi 2 belonging to a minus h and a, right. Now, if I define a is equal to x plus h, right, so then I get xi 1 is lesser than or equal to a, which is equal to x plus h, right, lesser than or equal to a plus h, which is equal to x plus 2h, right. Similarly, xi 2 is greater than a minus h is nothing but x, and xi 2 is less than a, which is equal to x plus h, right. So, this tells me that xi 1 must lie in this range, xi 2 lies in this range. If I combine these two bounds, what do I get for xi 1 as well as xi 2? So, this makes a statement about xi 1, about the bounds in xi 1. This makes a statement about the bounds in xi 2. If I want to make a combined statement on bounds, so I want to calculate bounds on both xi 1 and xi 2. So, I take the lowest value which is x, and the highest value which is x plus 2h. So, both xi 1 and xi 2 must lie between x and x plus 2h. So, then what do? We add these two, right. So, I add these two, so I get f a plus h plus f a minus h, then I get f a plus f a, that gives me 2 f a, this term cancels out. So, I have f a plus h plus f a minus h minus 2 f a if I bring that to the left hand side, right, and that is equal to half h square f double prime xi 1 plus f double prime xi 2, right. So, that is equal to this plus this, right, half h square f double prime xi 1 plus half h square f double prime xi 2. So, I have that term. Now, since f double prime xi is continuous, right, f double prime is a continuous function, right. So, the mean of f double prime xi 1 and f double prime xi 2 must be equal to the value of f double prime evaluated at some point between xi 1 and xi 2, right. So, f double prime evaluated at some point between xi 1 and xi 2, and therefore, xi must belong to the interval this, right. So, we know that both xi 1 and xi 2 belongs to this interval, right. So, the xi, so the function xi which is equal to the mean of these two, right? The function, I mean, if f double prime xi is the mean of this function, right? That xi must lie also in this interval, right? Is that clear? That xi must also lie in that interval, right? So, and this interval again I am expressing in terms of a and h, keeping in mind that x is equal to a plus h, right? Oh, sorry, a is equal to x plus h, right? So, that gives me a minus h, a plus h, right? So, xi must belong to a minus h and a plus h. Recall also that f a plus h minus twice f a plus f a minus h is equal to del square f a minus h. We saw that before. I don't know where we saw it, but we saw it sometime. Right here, right? Del square f x minus h is equal to f x plus h minus twice, right? So, f a plus h, this is equal to del square f a minus h, and a minus h is equal to x, right? So, that is equal to del square f x. So, what do I get finally? I get del square f x is equal to h square times f double prime of xi, where f double prime of xi is the mean of f double prime xi 1 and f double prime xi 2, and I know that xi belongs to the interval x to x plus 2h, right. So, again we are getting a proof for k equal to 2. Recall our original general expression, del k f x is equal to h k f k xi. So, for k equal to 2 also we have shown that this is true, right. So, del square f x is equal to h square f double prime xi, where xi again belongs to the interval x to x plus 2h. Remember, the interval we said was x to x plus kh, right. So, now it is exactly x plus 2h because we are looking at the second difference, right. Similar proofs can be obtained for k greater than 2, right. So, k greater. So, this is the relation between the difference operator and the differential operator, right. So, it is equal to the difference of the result of the difference operation, but evaluated at a point which is not exactly at the same point, right. So, from the general result del k f x is equal to h k f k xi belongs to x plus kh, we have that h to the power minus k times del k f x is an approximation to f k of x. Why is it an approximation? Because it is not evaluated at x, right? It is evaluated at xi, right? That is, if it is not exact because of this, right. So, it is just an approximation to f k x, and the approximation will be as good as the interval. As the interval becomes smaller, the approximation is going to become better and better. So, if x is very close to x plus kh, well, your derivative and the differential operator are going to be close. If not, they are going to be wrong, right. There will be errors, and the error you can see is approximately proportional to the step size, because the error is like kh, right. So, it is proportional to the step size. So, it is linear in h, right. It is linear in h. One more thing, in the computation of delta k f of x, we use the values of f at x, x plus h, x plus 2h up to x plus kh, right. And you will note that these values, this x, x plus h, x plus 2h, x plus kh, lie symmetrically about x plus half kh, right. So, all the function values that I am evaluating at these different points, right, they are symmetrical about x plus half kh, right. The points at which I am evaluating the function are symmetrical about x plus half kh. Now, it can be shown that h to the power minus k times delta k f x is actually a much better approximation to f, to the derivative the kth derivative evaluated at x plus kh plus 2, that is at the midpoint of my interval, in the midpoint of my interval, rather than at one end of the interval at x, right. So this operation, this operation which I got after operating on f k times with the difference operator, and if I divide that by the step size raised to the power k, I know that is an approximation to the derivative evaluated at x, right, and the error we know depends on the step size, but actually it is much closer, that it is less of an approximation if I evaluate the if I look at the point x plus kh by 2, right. It is less of an approximation if I look at the point x plus kh by 2 rather than looking at the point x, right. So at the center of the interval, if at the center of the interval the difference, the kth difference is much closer to the derivative than at the end of the interval. The derivative being evaluated at the center point, derivative being evaluated at the end. So again let me repeat. So if I look at the kth difference and I look at the derivative evaluated at the end of the interval, and I look at the derivative evaluated at the midpoint of the interval, the kth difference is much closer to the exact derivative of the function evaluated at the midpoint of the interval rather than at one end of the interval, right. So that is because it turns out that the error in this case, instead of being linear with the step size, is actually quadratic with the step size, right, if I am evaluating it at the midpoint, right. So the midpoint gives the difference is much closer to the derivative at the midpoint than at one end of the interval. So let's look at a little example, right, and show whether this is true. So in the example we look at is the exponential function f of x is equal to e to the power x, and so suppose we are going to evaluate differences with a step size of h is equal to 0.1, right. Then if I look at delta f0, delta f0 is going to be f evaluated at 0 plus h minus f evaluated at 0, and h is 0.1. So f evaluated at 0.1 minus f evaluated at 0 divided by my step size h, which is 0.1. So that is going to be e to the power 0.1 minus e to the power 0 divided by 0.1, which is going to be 1.05171. How close is, then we want to look at how close this value is to the derivative of f evaluated at 0. Well, the derivative of f evaluated at 0 is 1, right. Derivative of e to the power x is x, so the derivative of f evaluated at 0 is 1. So it is quite different. I mean, it's not quite, it's 5% off, right. So it's 1.05171 and here it is 1, right. But instead of evaluating it at 0, if I evaluate the derivative at, this should be 0.05, right, sorry, this should be 0.05, that is at h by 2, my step size is h, right. So evaluated at midpoint of the step size, right, midpoint of the steps. So remember, for the linear, for the first derivative, the interval size is x plus x to x plus h, right. So I am evaluating it at the midpoint of the, my first point is 0, my end point is 0.1, I am evaluating it at at the midpoint of that interval. So I want to evaluate it at 0.05, right. So if I evaluate e to the power 0.05, if I evaluate the derivative of e to the power x, which is the same as e to the power x, and if I evaluated it at 0.05, I get 1.05127, which is actually much closer to the difference than the derivative at x is equal to 0, right. Thus it is clear that h minus h to the power minus 1 delta f0 is a much better approximation to the actual derivative at x is equal to 0.05 than at x is equal to 0, right. It is much better approximation at the midpoint of the interval rather than at the end point, right. This holds true for, we just showed it for the first difference and the first derivative. It holds true for higher order differences and higher order derivatives as well, right? Okay. So let's take a step back now. So and the difference operator that we have talked about, the delta operator that we have talked about, is actually only one particular difference operator. There are many other difference operators, right? This delta operator, this delta difference operator, is known as the forward difference operator. Why is it called the forward difference operator? Because delta operating on f at x is equal to fx plus h minus f of x. So I have to look forward by one step h, and then I take the difference at f of x to calculate that difference operator. But there are other difference operators as well. For instance, we have things like the backward difference operator, the central difference operator, the average difference operator, and things like that, right? And it turns out that all these operators are related to each other. So let's take a quick look. So other difference operators include the central difference operator, the average difference operator, the backward difference. So this, for instance, we are going to denote by delta the central the central difference operator. So that is fx plus half h. So delta operating on f of x is equal to fx plus half h minus fx minus half h, right? Then there is the average difference operator mu, which operating on f of x yields half f of x plus h plus half f of x minus h. So at x I take half a step forward, I take half a step back, I evaluate the functions at those locations, I take the average of that, and I say that is the result of my average difference operator, right? The backward difference operator, on the other hand, is fx minus f of x minus h. So which I have denoted by this nabla sign, right? F of x is equal to f of x minus f of x minus h. So I am looking back now, right? Instead of looking forward, I am looking at x minus h. Instead of looking at x plus h, I am looking at x minus h. And even by just cursory examination, you can see that these difference operators are related to each other. For instance, the forward difference operator operating on f evaluated at x minus h is equal to the backward difference operator operating on x, right? And similarly you can relate the central difference operator too. So similar relationships exist between higher order difference operators as well. So we will continue with our discussion on difference operators in the next lecture. Thank you.